Welcome, everyone. This is the last talk of the day. And of course, when the going gets rough, you need somebody that can deal with it. And maybe Eric is one of the smoothest person I ever met. So it was a particularly good choice to put him here. It is my pleasure to introduce for you Dr. Eric Hall. He is currently working as a Baxter Fellow and lecturer in the Applied Mathematics at the University of Dundee, his beloved Scotland. Dr. Hall actually received his PhD in mathematics exactly in Scotland from the University of Edinburgh in 2013, and his advisor was John G., right? Yeah. Correct. Yeah, that was good. And since then, he has worked in several prestigious institutions, including the University of Massachusetts, yeah, and Hurst, and the EVTH, of course, in Aachen University, very prestigious as well, where he worked in our Math for UQ Alexander von Humboldt chair. Dr. Hall's research interests include uncertainty quantification, stochastic and predictive modeling, and numerical simulation for complex systems. He essentially is a numerical analyst for stochastic problems, right? Right. Thank you so much, and the floor is yours.
No, thank you for the invitation. Yeah, the cookies are gone. And I hate to tell you, they're about a third butter. So, you know, each one is like 20 minutes on the treadmill. So, right, so I'm going to start with unapologetic plug. So Dundee is an opportunity. We're hiring in mathematics. So Dundee, if you don't know, is this charming twee city about 35 miles north of Edinburgh. We have about... Dundee is the sunniest place in Scotland. We have... It is the farthest east that you can get sort of in Scotland. So it's about 35 miles north of Edinburgh. It's got about 12,000 undergrads and 6,000 postgrads, and our math division has about 17 faculty. Have more pretty pictures. So as I said, we're hiring in the department. You see lush green. It was originally a constituent college at the University of St. Andrews, which is just across the river. For a very small city of only 150,000 people, we have a lot of museums. This is actually the ship. This is the Discovery, the ship that went to Antarctica on the Antarctic expedition, taking Shackleton. You see, and this is the V&A, Victoria and Albert Museum, Dundee. It's very lovely. This is a view over the city from the giant volcanic plug that sits at the heart of the city. And as you see, we have an open position at the moment, and the applications close on the 11th of June. And in particular, right, we're interested in hiring someone who does optimization or operational research, stochastic processes, applied probability statistics. So maybe someone here is interested in applying. It's a really lovely place, and you'll get to be with me. Better or worse. Think carefully if I'm the sort of colleague that you'd like to have, I guess. So this is joint work with Raoul and Christian. It's a very old picture of Christian, but I like it. And this is published late last year. So what I'm going to tell you about, okay, are some weak error rates for numerical approximations that are involved in sort of these linear rough volatility models, so rough Stein Stein. And I'll give you a sketch to motivate our proof. Why don't I keep coming over here? I have a clicker. Right. The methods that we use in the proof are fairly elementary, right? So if you've been following the mini course, probably you know more about rough volatility models than I do at this point. So in our proof of the weak error rates, right, we make use of these Markovian extended state spaces, Taylor expansions, and conditioning. So things that you don't have to get your blood pressure up to think about. Right, so linear rough volatility. Right, so what's the point here is that, rough stochastic volatility, the whole purpose of this mini course, right, is this increasingly popular paradigm in quantitative finance because it addresses two empirical challenges, right? So the first being the time series, right, indicate that the log realized variance has hold irregularity less than 1/2. Maybe Eduardo thinks it's actually negative, but hey, let's go with this, right? The other is that you sort of have this, you recover the power law explosion of at the money implied volatility skew, which is what you see here on the right, right? So you have this power law on time to expiry as the maturity goes to 0. Right, so these two things taken together, right, so telling you that the log realized variance behaves like fractional Brownian motion, and typically the Hurst parameter is small, so like 0.1, 0.07, something like this, right? So how should you model that? Well, that's the point of this rough stochastic volatility models, and we saw a couple different sort of classes of these models, one being sort of the rough Heston, yeah. Another class, which we'll talk about now, is sort of like the rough Stein Stein or the rough Bergomi model, where instead of having this SDE for your stochastic volatility, you have an explicit function of your fractional Brownian motion. Okay, and of course, right, then we don't have any Markov process, and this is a challenge for both theoretical and numerical simulation. Yeah, right. Yeah. If you want to know more, of course, you can look at the nice paper by Eduardo. Right, and the rough Bergomi, this we saw earlier in the mini course, right? So again, this is sort of the same type of thing, right? We have an explicit functional dependence on the fractional Brownian motion, right? And the whole point here is that if we want to use these models for option pricing, then we need some simulation-based methods, and we need a numerical analysis for these simulation-based methods. So what can one do? Well, essentially, right, what you're interested in is approximating stochastic integrals like we have here on the left, right? So the stochastic integral of some functional of a function of fractional Brownian motion. If we were to think of doing just like a left point rule, right? Have the thing on the right. Now, if we have this rough Bergomi model, right, we know the strong rate of convergence is H. And what's the trouble with this? Well, I mean, we're interested in the weak convergence. We hope that it's not as bad as the strong convergence, right? To understand if sort of, yeah, I mean, so for why do we hope that it's not as bad, right? Well, for sort of standard SDEs, where you imagine like H is a half, right? You'd have weak rate 1, strong rate 1/2. If the right, if the weak rate, which is the thing that we're after here, sort of is H is small, and suppose the rate is depending on H, right? If you need sort of n time steps to reach an error tolerance of epsilon, then to reduce the error tolerance by a factor of 10, say, the number of time steps increases by 10 to the 10, right, in the asymptotic limit. So in order for this to have sort of a, for numerical methods for the weak, for these observables like expected value of the payoff, right, to be viable, right, we sort of want to find some rate, any rate that isn't just H, right? Yeah. Of course, so Cheheb and Christian and Raoul, they use some discretization-based methods successfully, right? In fact, they even found sort of a rate that was stable enough that they were able to extrapolate, right? So to do some sort of Richardson, right? Extrapolation. Right, so the viability, yeah, so old, 2020, ages ago, yeah. The viability of numerics for these option pricing problems depend on there being a rate that doesn't, depend on h, right, by itself, right? We have h plus a half, something like this, it's okay. So when we started this, we talked to people and there were many conjectures about what the weak rate might be. In particular, some told said, no, the rate will be 2h. And some people said, no, the rate will be h plus a half. And some people, said, no, we think it's maybe 1. Clearly, these we'd be happy with, right? If we want to be able to estimate the weak error. 2h would be a problem, right? I mean, it's not this as bad as h, yeah, right? So good news is that it depends on h. I can tell you this, but how? So we find, using our sort of simple methods, a weak rate h plus 1/2. Okay, so this isn't as bad as h by itself, right? So specifically, if you're sort of considering this x here, where it's a direct integral of a fractional Brownian motion, in particular the Riemann-Liouville fractional Brownian motion, and you're considering a left point scheme, then we find, that the weak error is on the order of delta t to h plus 1/2. Yeah. Okay. Before giving you an idea of the proof, I'll share some numerical experiments and maybe something a little exciting, because this is not the end of the story. All right, so the weak rate increases as h increases. So here you have some simulations, both for small values of h, the Hurst index, right? So here on the left, we have some simulations that use 0.05 for the Hurst index. On the right, there's some simulations with 0.15. So h is small. Back here. Right. So we just want it to be sort of smooth. Okay, so we want it to be that we have continuous and bounded, right? The exciting, when I said there'd be something sort of exciting coming, it'll have to do with phi. Okay. Right. So the weak rate we see here, it depends on h. So sort of as in delta t, right? As delta t goes this way, right? We see the h. Okay, so what do we have here? So here in green and here in blue, right? These are two different payoff functions, phi. Okay, so for each of these, this one here is one choice of h, Hurst index. Here on the right is a different choice of h, and the difference in the lines are the payoff functions. Okay, so here's a sort of bizarre choice, I guess. Here's x cubed, and here's the Heaviside function, which doesn't even really fit in our theory, but nevertheless, you throw it in. And you see here, this is the best fit slope to these points, and it's 0.16. And in the variation in our samples, it could be as low as 0.64, as high as 0.7. Okay, but you can certainly say that it depends on h. H plus 1/2 it's consistent with. Could also be consistent with 2h plus 1/2 or 3h plus 1/2. But for both of these, right, small values of h, right, we see this sort of similar behavior. And here, when h gets bigger, right, you get a slightly higher slope for each of these. Okay, so this is the weak error. In particular as well, something you had to sort of be a little careful about here is the overkilling the sort of reference solution, because we have no real solution here. If you sort of don't do that, you get really funny curving down of the lines, as you do with most anything, right? Okay, here's a different picture. On the left, in this experiment, okay, here we have h very tiny, 0.05, but we've chosen phi to be a quadratic function. Here we get 1. Right? And here is also for a quadratic payoff, and you different h. So here's 0.05, here's 0.15, and you also get something that's sort of consistent with 1. And then here on the right, this is what happens if you take h as 0.5, right? That would just be sort of a standard Brownian motion. And then you also get a slope that's sort of consistent with 1, right? For any phi that you choose, any observable, which is what you would expect, right? Because that's the weak rate for an SDE when you're having the Euler approximation. So the sort of exciting thing is that it looks like the weak rate depends a bit on the payoff, right? So typically, right, you'd expect if you change maybe like the regularity class of the phi, that then the weak rate might change. But this has not changed the regularity class. I mean, this is just another polynomial. So the sort of nice thing about the simple proof that I'm going to give you an idea of is that you can sort of see really easily in these Taylor expansions when you have phi as, you know, a quadratic function, higher order terms in the Taylor series are 0. So you get rate 1, not bad things, yeah, like h plus a half. Yeah. Oh, and here's another experiment. We took not, so on the left here, okay, we took not a quadratic payoff, but we took a shifted cubic, and you get something that looks like rate 1, right? So, I mean, so here with the shifted cubic, right, you have something that's better approximated by a quadratic, right, than the support to the distribution of the underlying. So there again, you sort of see that it's sort of acting like a quadratic, right? So it's a really, I'm showing you these because it's a really subtle problem. If you just were sort of doing this, you can understand, okay, I get why a lot of clever people told us it should be 2h and it should be h plus a half, and it could be 1, right? Depending on your particular problem and what you did, you might have a very different intuition about what's going on, right? So it's a very sort of subtle problem. It's really interesting, I think. The rate that I'm going to share with you, in fact, a lot of people work on this. It's not even the best rate, okay? But I like our proof. It's simple. I understand it. Yes. Uh-oh, a comment. If you're going to say I don't understand it, have words. Yeah.
No, I mean, actually, the comment that I wanted to make was that there is a very, not really implementable, but if you, instead of this left point rule, you take the conditional expectation on the Brownian motion as sampled on your time grid, then you actually can show that this has rate 2h. So this scheme, which you would think of, which is in the strong sense the best possible, actually in the weak sense is much worse than the others. And again, it's not really an implementable scheme because you don't know this conditional expectation. It's just, you know, this is indeed sample. I completely agree.
Yeah. Yeah, so that was what was here on the left, was this shifted cubic that suddenly you can sort of make strange things happen. And this was comparing for the same sort of level of h, right? With just the cubic, you see suddenly you shift a little bit and the slope is, I mean, the rate you find, the empirical rate that you observe is very different. Okay. But I mean, the other thing, on the other hand, it sort of leads you to believe, okay, we'll be all right. You can probably find some viable numerical methods. So, not all is lost, right? Okay, and this is all just I said, right? The shifted cubic payoff achieves a higher rate than the cubic, as the shifted cubic is better approximated by a quadratic than the support of the underlying. That's our, yeah, so that here's sort of something saying that, right? So in particular, right, if you have a quadratic payoff, then you can get weak rate 1, right? And you can see this with the method that I'll show you. Okay, so how do we prove this? It relies very much on the things that you've seen in the mini course, right? So this affine approximation of the fractional Brownian motion, and then other ideas that are pretty standard. Why do we start with this, right? So, I mean, this sort of general roadmap of the proof, right, is that you use this affine representation, right, of the fractional Brownian motion. This is sort of a classical thing. And then we're going to approximate the affine representation, right, using a quadrature in the parameter. Yeah, so you saw that you had these speeds of mean reversion parameters, and we even used the same letter Y as Eduardo was using in his talks, right? And then you can use this once you give an approximate affine representation, right, to obtain what we call a Markovian extended state space. Why do I call it that? Well, in other areas of science, so when you're talking about generalized Langevin equations and things like this, it's the same sort of idea of a technique, right? You have generalized Langevin equations related to these stochastic Voltaire equations. Last year, we made a calculation to show they go from one to the other, right? Yeah, they like to call these objects extended variable systems, extended state space systems. You'll see why we go through the sketch of the proof. Right? We do the sort of things you would expect to do when you're showing weak error rates, and you've ever maybe worked with Anders Sepeschi, someone like this, right? You write the discretization error as a telescoping sum in the value function, right? And then you obtain the error rates by using conditioning, right? Conditional expectation. And as I said, right, sort of the mechanism by which you get rate 1 for quadratic payoff functions is really easy to see in the Taylor expansions, because they involve payoffs phi and derivatives of payoffs phi and second derivatives. And if it's quadratic, everything that's higher than the second derivative is just going to be 0, right? Okay, so what's this, just to remind you what I mean when I say this affine representation, right? So the fractional Brownian motion, right, admits this representation as a linear functional of an infinite dimensional family of Ornstein-Uhlenbeck processes that are indexed by some speed of mean reversion, right? Those are these YT thetas, okay, where theta is the speed of mean reversion, right? So all I'm saying is that for this fractional Brownian motion, right, for this Riemann-Liouville fractional Brownian motion with h between 0 and 1/2, right, you can express this as an integral of OU processes YT that depend on theta, which is the speed of mean reversion. Here I've plotted you a sample, right, of here on this axis it's t, and here on this axis it's theta, and you know, it's actually in the theta direction is a nice analytic function, right? That's fantastic, right? It means you can sort of imagine writing down a quadrature rule for this in the theta direction. Right? You can approximate this integral, yeah, nicely. You could write down any sort of rule you'd like, quadrature rule, and get whatever degree of accuracy you'd like. There's no barrier to this. Yeah. Okay. So right. So this was our y of t theta. Let's see here on this axis it was t, on this axis it was theta. It's nice and analytic function of theta, right, in the theta direction. Only thing, right, and this was for h is 0.07, so it's pretty rough, you see. So what happens, right? So we write down our approximate affine representation. So basically, we take a quadrature rule. I'm not going to really specify precisely which one to take, because you could take it as you like, and we truncate. Or so we have a collection here of Ornstein-Uhlenbeck processes that are indexed by our speed of mean recursion theta L, and we take NL of them. Okay? And in particular, right, the fact that you have this sort of I mean, this sort of this WH hat converges to this WH. I guess this is this paper by Philip Harms. These strong rates of convergence for Markovian representations of right. So this is sort of well known. And then we can say, all right, so we split then our weak error, right? So this is our payoff of our underlying, and I write it here just to emphasize, right, it's not an actual functional relationship written here. It's just to emphasize which process I'm talking about, right? So here, right, we have the error between, taking our underlying with WH and with the affine approximation. This is controlled because of the strong rates that Philip Harms has given us, right? Here, this is the numerical approximation to our underlying with with our affine approximation, and the numerical approximation of our underlying with our true WH, and that's controlled, right? This is the thing in the middle, right, where we'll get our rate in delta t, right? This is basically the only thing that depends here on a difference between a continuous guy and the discrete, right? So this is the quantity then that we'll look at, and you'll see here that it's nicely, right, depending on just our affine approximation, approximate affine representation. Okay. Just one other thing I'll mention, right? So, I mean, clearly when you're thinking about this sort of which process am I using, right? Then you want to think in terms of sort of WH hat. But when we go to write down Taylor expansions, we're going to want to use our individual variables in our extended variable state space. So we'll also sort of introduce this notation S for y of t, which is just this quadrature rule, right? The sum of the yt variables times delta t. Yeah. Okay. So Markovian extended variable system, right? So the idea is that we substitute our approximate affine representation into our underlying, yeah? And then we want to consider this dynamics, right? So we have our x hat and all of our NL degrees of freedom. So our z then is in NL plus 1 dimensions. And we write down Euler discretization for our z, okay? So in particular, right, that's looking like this, right? So we have our x bars, depending on this quadrature rule of our y's at the left-hand point, dws, okay? And then for this, right, dynamics, we can formulate our Kolmogorov backward equation, right? So sort of assuming maybe that this phi of zt is smooth and bounded, right? You can get this value function u of zt, right, which is just this conditional expectation, right, of phi of zt given that you start at some z, yeah? And in particular, right, this x hat that comes into it. Okay, don't think, I mean, here this is just sort of assumption made to make writing this down easier, but it's not really some, it's for convenience, right? It's not a barrier to progress. Right, and so then what you want to look at is representing your weak error, right, as a telescoping sequence of local errors. And then we think about what is this local error in terms of our Kolmogorov backward equation. Okay, so here we have, I've written down this is our weak error, right? I've written it down as a telescoping sequence, right, between all our time points. Yeah. And we express this local weak error using the Kolmogorov backward equation. Okay, that's what's written here on the first line. Here, right, you have just your sum of your y's from ti to s, right? So it's this sort of increment. Here we wind up with, in fact, something that's the sum at s squared minus the sum at ti squared. So we've just sort of used this notation to indicate that, yeah? Now, what do we do with this? Yeah. So here we have some derivatives of our Kolmogorov backward equation. Now you can compute these using directly, right? You just directly compute these fluxes. And you wind up then in the end with sort of two terms. Yeah. And here, right, when you compute this flux, you see that it's exactly this, right? So we have a conditional expectation of two derivatives of our payoff of x hat of t, given that you start here at zs bar. This thing in here, right, we're going to want to understand, and we give it a name, nu. And then similarly here, when we compute the sum of all these fluxes, we wind up with another conditional expectation, which is the same, except there's some other terms here. And this we'll call nu tilde. Okay. So we get two terms, which I've written here sort of j and j hat. That'll come later when we look at what happens when you have quadratic phi. You can make a very nice straightforward calculation. And all we've done, right, is just use the idea that you can write down your weak error as a telescoping sequence in the value function. This is not, right? Probably you've seen similar things for weak error rates for other problems, right? Then what? Well, in particular, right, we want to look at writing down a Taylor expansion for each of these terms, yeah, in delta t, right? So we Taylor expands each of those nu and nu tilde terms at ZTI, and then apply a conditioning argument, right? So basically using the fact that you have that this C bar is linear with respect to increments over Ti to S. Yeah. That is, right, you can sort of write this difference here down as that, right? Then you can imagine doing a Taylor expansion of nu at ZTI, yeah? So here we have, right, that it's the nu at ZTI, right, plus the sum of higher order derivatives times this guy gets picked up, right, and then each of these, so we're summing over some beta, and then you have a remainder term. So I mean, so these are the new terms, right, are importantly these conditional expectations, right? So these are deterministic functions, right, of these FTI measurable random variables ZTI. So when we plug them back in, right, to our terms in our expansion. Here's just the first one, right? You see that we get quantities that have expected values here that we can measure, right? Or that we're going to calculate explicit things, right? So in particular, all the terms that are sort of left here are terms that contain some increment. Yeah, you see here, only the conditional expectations here contain increments, right? So here's the only places where we're going to get delta t in the estimate. Okay, so then the idea is that you want to sort of isolate the delta t, okay, in each of those. And then the sort of the key to actually getting the expansions, though, is of course a little tricky. Namely, it's that you need to make sure that you're sort of, because remember, this is a quadrature that involves a sum over delta thetas, right? You need to make sure that things don't go haywire with the delta thetas, right? That you don't lose summability, okay, with respect to delta theta, with respect to the thetas, right? So yeah, again, after sort of isolating the order in delta t using these expansions, the only really tricky part is to show that the coefficients that you get in the expansion are controlled with respect to these speeds of mean reversion. So, for example, right, when you have these, imagine you have a quadratic payoff, all those higher order terms, right, in fact, vanish, and you're only left with the two terms that we sort of showed before, okay? So you can work sort of directly with these increments to sort of express, right, this square of the different remember this s of y tis squared is the following notation, right? It's you have the sum of the y's at s squared minus the sum at ti squared, okay? But the important thing is, right, you're able to sort of express this, right, directly in the extended variables. So this increment, right, you're able to sort of, for this conditional expectation, you're able to directly express this using facts about OU processes, which you've seen many times this week, right? So it's not too horrific, yeah? And then from this, you're able to, right, sort of directly measure the order in delta t, okay? And again, the only sort of tricky thing is that you need to make sure that, you know, this thing here that depends on the thetas is still summable, right? If it's not summable, then you don't get delta t, yeah? You get something with infinite, yeah? Right, and so remember that this was for our telescoping expansion. So it's still a sum over t. So everything will get divided by t in the end, and you get just, sorry, delta t in the end, and you get just delta t, not delta t squared, right? So here it is. So when you return to your telescoping representation for the weak error, right, you can put in all those, you can plug in your right, your bound that you get for each. You're summing up over each I from 1 up to n minus 1. So in the end, you get that sort of this is divided by delta t, right, because of this sum over the t's. Yeah. And I mean, we actually have what the constant is here, right? And this is weight rate 1 when you have these quadratic payoffs. Yeah. That's not it's not so bad. Yeah. So to summarize, right? If you're imagining, right, you have these problems where in principle what you have is some, you know, functional of a fractional Brownian motion, right? So you have the stochastic integral of the fractional Brownian motion, and you're imagining using the left point approximations, this Euler scheme. Then, right, this converges with weak rate h plus 1/2. Unless the payoff phi is quadratic, then we see that it's weak rate 1, and that's strange, but it's what happens. Yeah. Right. Yeah, it's strange, but it's what happens. Now, a few remarks, right? As I showed, this problem really is subtle. So, if you do try and repeat any of the numerical experiments, just keep in mind, right, that, it's kind of hard to distinguish rate, 1 empirically from what you might see, right, for the weak rate. H plus 1/2, 2h plus 1/2, 3h plus 1/2. In particular, so I guess the best rate also for these linear rough volatility models, as I've seen in the literature, is 3h plus 1/2. That's by Paul Gassat. And there he's using Malevin calculus to get the rate. We don't have a lower bound, right? So this is consistent in some sense. Yeah. I never said that it was the best rate, right? Just a weak rate that one found. Yeah. Right. Yeah. Yes. Yeah. Yes. Right. It's yeah. Yeah. Yeah.
Maybe a comment. There is actually a lower bound in the paper by Thomas Wagenknecht.
This is even newer.
Yes.
You heard about it last week.
The case cubic payoff in the linear case 3h plus 1/2 minimum 1 is optimal.
Oh, with a cubic. And does it say anything yet about sort of this sort of action? Like if you have the shifted cubic, what happens?
Well, I mean, the thing is, for the cubic, you can actually calculate the expected value of this.
Okay.
I mean, it's like a display sum.
Yeah. It's a very active area, and it's fun. Oh, and it was Antoine also had a paper. You were there, weren't you, last week? You say there was another paper that I have not seen yet. They don't get that one. Okay. Yeah. So there's, it's if it's something you're interested in working on, it has lots to think about, and it's a hard problem, right? I guess when we first started working on this, Christian was very ambitious and thought, yeah, finish by Christmas sort of thing. Okay, right. So so the key points sort of are for the left point scheme, right? You can sort of find this, we find, right, a weak error rate of h plus 1/2 for general payoffs, but rate 1 for quadratic payoffs. And again, that's a funny thing, right? Because you don't anticipate that if you just change from one polynomial to another, you get a different rate, and it seems other folks get similar, yeah. Our proof relies on just Taylor expansions and using this affine Markovian representation of the underlying, from these, in particular from these Taylor expansions, these asymptotic expansions, you can observe, right, the mechanism by which you get rate 1 when you have quadratics, which I think is kind of fun. If you want to go to the full Bergomi, right, I guess, right, so here I'm saying nonlinear psi, right, so if you have this functional of the fractional Brownian motion. You remember that was sort of the difference between the rough Stein Stein and the rough Bergomi model. Made it possible to sort of extend this, but the formulas just get a little tricky. I've not had yet the constitution to sit down and think about it. Right. So yeah.
There's a work.
There is already a work. Is that you also heard about this? Path affinity. It was Antoine. Yeah. See, so fascinating. Yeah. So thank you, and just again, really, if anyone's interested, it's coming up soon. But yeah, I think if you've worked with AJ or Raoul, then you have sort of the constitution to do really good things in a small department, right? So, yeah. So, thank you.
You made it so enjoyable that I want to look at it.
Yeah. Yeah. I was going to put, yeah, please. Yeah. The fractional kernel. Right. So, I mean, will we make, yeah, that's a good question. Right. So, I mean, sort of the root of this idea, I think, is you know, taking this affine. I mean, the only place it shows up, right, is when you make the affine approximation, and then that's it. I mean, in particular, this sort of idea, right, of taking a extended variable system and analyzing that is precisely the thing that you use when you're thinking about generalized Langevin equations. Yeah, you have, as long as you have the affine representation, you're just taking Taylor expansion. I mean, I guess, yeah. Yeah. I mean, in the end, you just need to be able to make sure that when you make estimates, okay, so I say it's simple methods, right? But in fact, if you slip and make it the wrong place, any sort of estimate, you can clearly get things that are better in delta t, but then the thetas aren't summable anymore. Yeah, we know. Many weeks of and I believe, in fact, like the constant that we got there using the Lipschitz argument when it's the first term, right? When we have, for example, it showed some calculation when it was phi was quadratic. That I think is very sharp. So I'm sort of surprised that, yeah, well, yeah, so it works as long as you have sort of this affine representation. Everything else is just using Taylor expansions and then making a conditional. Does it matter when you take? No, I think it's okay.
Where we actually make an estimate of a sum based on an integral, and there we make an inequality. And I think this is where we actually
where we don't, the step where we don't get three, yeah. So it's a good story about sampling bias, I guess, right? We sort of talked to people and we said, what is the rate? And they said h plus a half. And then we found h plus a half and we were happy. And we probably didn't look hard enough for 3h plus a half. Yeah. Yeah, and I guess in some other ways, I mean, we're sort of just excited to have something that wasn't dependent on h alone, right? Because h plus a half, you have viable numerical methods, I think. So, yeah, it only uses the affine representation. That's the only place the kernel comes in. Yeah, maybe it's not probably a similar estimate, and they just said, nah, I'd rather go to dinner than. So I was going to put more details on the slides, but then I said absolutely not, because it's been a long week, and if we end early, no one will be angry. Yes.
Actually, it is a weak expansion, and we close it with a strong argument. And the number of terms that you have to solve with the weak expansion is related to the inverse of H. But that was still okay.
Yeah. Yes. So how many terms do you need in theory for the Taylor expansion? You can estimate it. Yeah. So yeah.
It's not sensitive because of this strong argument.
And even that, I don't know if it was super precise. It worked. It's enough. Yeah, no. There's a rate. Yeah. Go ahead.
So you use this affine representation, then you discretize it by a finite dimensional Markov process. Where is this step necessary? Can't you do it with the infinite dimensional representation?
I wanted, well, I mean, yeah, I guess, and then you could write down the, I mean, that's the idea with, well, yeah, the path dependent, yeah, PDE, yeah.
We're using this kind of old Talay representation of the vector, and you know.
I mean, at the other end, I mean, is it really the case that you need infinite number of them? I don't know. So on some sense, I mean, I was coming to this thinking of generalized Langevin equations, and I used these ideas, right? So there are many things, I'm sure, which are possible. I like, though, right, that if you think about it like this, you could talk to people who also do generalized Langevin equations, you know, open Hamiltonian systems, these sorts of things. They use very similar methods and similar language. Yeah. Sure.
The estimate was uniform in the number of theta that we use. Remember that
Yes.
we didn't say, you know, for many of these that
Yeah.
in principle you could pass to the limit.
Yes, this is also true. Yes.
We didn't say it is there because the estimate is uniform.
To be fair, if we hadn't done that, the proof would be wrong.
Yeah. Yeah.
Of course, if it wouldn't have been uniform, that would have been wrong.
Right. Okay. Are there any more questions?
No, we are done for the session. Thank you.
The 11th of June.